All right. Welcome, everybody. Happy final remote Wednesday. As I mentioned yesterday, we're going to do a pretty straightforward lesson today, just comparing two proportions to one another. So we've built up to this. We started by talking about single means, difference of two means, most recently, a single proportion. Well, now we have two populations that we are comparing those two proportions to one another. So let's get into this here. We can see our two targets, pretty consistent with what we've been doing in the last several weeks. Calculate a confidence interval for the difference of two proportions and that two sample z-test for a proportion. Our first few slides are a little bit wordy here, just giving us the background to what we're doing. We talked a little bit about the notation in terms of the population parameters and the sample statistics. We're using the subscripts 1 and 2 for our two populations. However, you'll see in our first example problem that you're welcome to adapt those to be relevant to the problem. And so if you're comparing like A and B, use A and B as the subscripts. You don't have to use 1 and 2. Remember that the population proportion is P, the sample proportion is P hat. Now, this is based off of our rule for our sampling distributions. And it's the same types of things that we've seen before in terms of our conditions. We know that we need a simple random sample. We know that these two populations, just like we saw with the difference of means, they need to be independent of one another. Excuse me. And when you're finding all of these theoretical samples, okay, you are comparing the differences between those two. Again, we are testing to see if there is a significant difference between population 1 and population 2. Now, what this rule says is that when these samples are large, this distribution should be approximately normal. Okay? And we'll see what exactly our normal curve looks like on our next slide. But right there at the center of this distribution is going to be this difference, P1 minus P2. And the standard deviation for this distribution is just a slight adaptation to accommodate two different populations. And previously, under our square root, it was just P times its complement divided by n. Well, now we're updating that to add on the second population proportion times its complement divided by its sample size. So this is what that distribution would look like. Right there at the center of the curve, we have our values for the differences, p hat 1 minus p hat 2. We have our standard deviation. We know as this equation that we just derived. And we are placing ourselves on this sampling distribution. So to turn this into something a little bit more practical for us is the confidence interval. So we say a large sample confidence interval is found by, once again, tweaking that standard error equation by substituting in our known values of p hat rather than just p. We know our sample values. We don't know our population parameters. So we're just substituting in p hat 1 and p hat 2 into the relevant locations there and there. Okay? We're still following the same basic format for our confidence interval. This shouldn't say estimate. This should say p hat 1 minus p hat 2. Okay? That's at the center of our confidence interval, plus or minus the z star. Okay, we have our chart for determining what our z star value would be, but typically for 95% confidence, either 1.96 or just 2. Now, large sample confidence, we want to be substantial with our sample sizes. We know that this isn't a t-distribution, that you can get away with smaller samples, but it's really not that bad. Okay? The rule of thumb is that we want at least 10 successes and 10 failures in both samples. Okay? So you see our ratio right there. It's not that difficult to get that for our comparison, although our second example that we're going to look at does not fulfill that requirement. Okay? In that case, you just need to be cautious about interpreting the results that you get. And something like that goes towards the robustness of the test. So we can see our confidence interval equation right there. Let's take a look at an example problem. This is about marijuana use in high school, and I'll read this. It says the Youth Risk Behavior Surveillance System monitors health risk behaviors in U.S. high school students, like tobacco use, alcohol and drug use, inadequate physical activity, unhealthy diet, and risky sexual behavior. Approximately 9% of youth have tried marijuana before reaching the age of 13 years. We want to know, how does marijuana use change over the high school years? So in 2013, they did a survey that randomly selected 3,500 ninth graders and almost 3,500 12th graders and asked them if they had used marijuana one or more times during the previous 30 days. Of these students, 620 of the ninth graders and 969 of the 12th graders said yes. We want to find a 99% confidence interval for the difference between the proportions of all 9th and 12th grade high school students who smoked marijuana at least once in the 30 days prior to the survey. All right, so let's look at our data here. You can see that rather than calling them population 1 and 2, let's just use P9 and P12. It's a little easier to keep straight what's what. So we want a 99% confidence interval. In the middle of our slide, we can see our two sample proportions. The proportion of 12th graders, 969 out of 3497, is about 27.71% said they had used marijuana in the last 30 days. For the ninth graders, 620 over 3,500, 17.71%. Look at that, exactly 10% less than the 12th graders, down to the hundredths of a decimal point for the percentage. So those are our two sample proportions. We want to know if that difference of 10% is significant across these two samples to say that there really is a difference, or this is how much it grows from the ninth grade year to the 12th grade year. So for our confidence interval, we see the standard error calculation in the center there, substituting those values in. I'll show you the technology in a moment. So at the center of our confidence interval is those difference between the two proportions, turning it into 10%, 0.10. There's our Z star for a 99% level of confidence, 2.576. So gives us a confidence interval of about 7.45% to 12.55%. So interpreting this in terms of like everyday language, we're 99% confident that between 7.45% and 12.55% more 12th grade students use marijuana in a month than the ninth grade students. Okay, that's how much it grows over that 4-year span. Any questions on this? All right. With the calculator, you can see it's pretty straightforward there. You have to scroll down a good bit in that stat and tests menu, but this is option B, a 2 proportion Z interval. And you can see you're just entering the values that make up the ratios. Make sure you keep them straight. In GeoGebra, again, same thing, level of confidence and the values that make up the ratios. Now for the hypothesis test, think back to what we did for the difference of two means. Rather than have a null value, instead, our null hypothesis was saying that the two proportions were equal. They're the same. I guess for means, it was that the means were the same. For us, the two proportions are the same. And again, that's the same as saying that their difference is 0. Now, the alternative hypothesis is going to be, if it's just purely interested in a difference, a two-sided, not equal sign there. If we have an implication of direction, then we'll use the greater than or the less than symbol. What is unique about the hypothesis test equation is that we have a standalone p hat. And remember, we're working with p hat 1 and p hat 2, but in this case, p hat by itself is the pooled proportion, meaning that you're adding the number of successes, so like x1 plus x2, divided by the two samples added together, so n1 plus n2. You're going to see that pop up in our equation here. P hat by itself in the hypothesis test is the pooled proportion. So our actual equation for the z statistic, we see right here in the middle. Again, all of our conditions, simple random sample, independent populations that are large enough. Okay. We see our z statistic here. The difference of the two sample proportions, p hat 1, p hat 2, goes in the numerator. Down in the denominator, square root of p hat, our pooled proportion that we just spoke of, times its complement, multiplied by 1 over n1 plus 1 over n2. Okay, adding the inverses of the two sample sizes together. And you see in the bottom of the slide there, the direction of the alternative hypothesis. So I have, I think, a pretty relevant and interesting example problem for us here, even though it is 10 years old. In May of 2010, the news magazine Slate surveyed readers to see if they remembered details of political events from the past decade. Unbeknownst to those surveyed, one of the events shown to each participant was fabricated, making this the largest false memory study conducted to date. The hypothesis of interest was whether political preferences guided by the formation of false memories, as memories have been shown to be more easily implanted in memory when they are congruent with a person's pre-existing attitudes. Okay? So in other words, you have these preconceived notions or beliefs or political leanings. If you get information, whether it's true or false, that goes along with what you already believe to be true, okay, you're more likely to embrace that and remember it as something that actually happened. Okay? This speaks towards our dissemination of misinformation in this day and age, fake news, that sort of thing. So this particular question was about the aftermath of Hurricane Katrina in 2005. And President George W. Bush, he was criticized for his lack of an immediate response. So as part of this question, they photoshopped this picture that you see here of Bush with Major League Baseball pitcher Roger Clemens. And they were supposedly, in the days right after the hurricane hit, they were at Bush's ranch in Crawford, Texas, and Bush was entertaining Roger Clemens and showing him around. That did not actually happen. But when they put this as part of their question, people felt that, oh, this falls in line with Bush not acting fast enough. This seems to, I remember this. Yeah. And the numbers here, it says it was viewed by 616 participants who categorized themselves as progressives. 49 participants categorized themselves as conservatives. The event was falsely remembered as having occurred by 212 of the progressives and 7 of the conservatives. How strong is the evidence that a larger proportion of progressives have a false memory of this event than conservatives? Now, we'll talk about these disproportionate sample sizes in a moment here, but let's look at our data here. So the hypothesis is that there's no difference between the proportion of progressives and conservatives who falsely remembered this. P hat 1 is the progressives, P hat 2 is the conservatives. Our alternative hypothesis is that more progressives misremembered this than the conservatives. So we can see what the data shows. Our sample proportions for the progressives, 34.4% of them remembered this, even though it didn't actually happen. For the conservatives, 14.3%. Now, we also see that pooled p hat that I was talking about. And you can see how they're adding the 212 and the 7 in the numerator, and you're adding the two sample sizes to each other. Now, here's a good point. Notice the differences between those two sample sizes. Okay? Only 49 conservatives. That tells you a little bit about the readership of Slate. It definitely leans liberal. So you only have 49 conservatives reading this. 7 of them remember reading about it. Okay? It tells you a little bit about what's going on in terms of possibly biased results. Anyway, our Z statistic, we see the calculations right there. Turns out we get a Z score 2.88. 2.88 standard deviations above the mean for this differences of proportions. That corresponds with a p-value 0.00199. We have pretty strong evidence that among this survey's audience, progressives are more likely than conservatives to have a false memory. Okay. Now, that is for this particular question. Okay. I would expect similar results if we had something that played into conservative beliefs as well. And again, this lends itself towards the proliferation of misinformation that's being spread. People see something online that may or may not have happened, but it falls in line with their preconceived notions. It supports their beliefs. It's that confirmation bias that I've been talking about since the beginning of the year. Okay. So they believe it to be true because they want it to be true. And they spread it and they share it, and more people believe it. Right? You can see how it plays into our polarized, politicized climate. Just showing you the technology right here. Our two proportion Z test on the calculator. It's on our first screen. You can see it there. Just provide the ratios and the direction of the alternative hypothesis. With GeoGebra, again, same sorts of input. Anybody have any questions with this? All right, so we did have a homework assignment due this morning. The key for that is available on Canvas. And we may talk about that a little bit on Friday, but we have our next homework assignment coming due on Friday at the end of the school day. Friday during class, you will have the entire class period to work on this assignment. Okay. So you can feel free to get started on it, but I wanted to make sure that we got it done before we went on spring break. After break, we'll have a little project. We'll spend several days making sure we keep these tests straight. All right. Have a good one. You're free to sign off. I'll see you guys.